Assalamu alaikum everyone. In the previous lecture, we learned the standard integration results for x to the power of n if you're integrating it with respect to x. And then we also did if exponential is raised to some power of x, some function of x. And we also did a reciprocal function where the denominator was in the linear form 1 upon ax plus b. And if you are integrating it with respect to x, along with basic trigonometric and definite integration. So in the last lesson, we did all of that. Those rules work when the expression is already in a recognizable form. So these are recognizable forms. Now, today we deal with expressions that are not yet presented in a useful form. For example, if I give you x multiplied by x squared plus 4 to the power of 2, and I ask you to integrate it with respect to x. Now, a few of you who will be smart will say that, okay, you just expand the bracket and do it. Yeah, that's right. But so for all the smarties out there, what about if I raise it to the power of 11? Now what you're going to do? Okay, so there is no direct formula for this exact expression, but it has been constructed very deliberately. Inside the bracket we have x squared plus 4, and directly outside it we have x, which is closely related to the derivative of the inner function, which is 2x, right? So that relationship is the clue. Integration by substitution, and hence we land at integration by substitution. Okay, now, so this is not really about replacing letters for the sake of it. We don't really want to just, substitute x squared plus 4 for you. We don't want to do it. I mean, just for the heck of it. It is about transforming a difficult looking integral into a standard integral we already know how to solve. That's it. Now, the decision that you must make first. Okay, now let's see. So, you must think about that which part of this expression would make a useful new variable. Like, so for example, usually you choose the part that is inside the power. I mean, just like here. So you'd rather substitute this thing inside the power, right? You would try to change something which is inside the under root, right? If it is inside an exponential, maybe 1, 2, 2 was if this was inside the power x squared minus 4. I don't know if it is 2x cubed minus 4, something of that sort. So you are going to substitute this. In this case, you're going to substitute this. In this case, you're going to substitute this. I'm just suggesting. Or maybe if there is something inside the logarithm, right? I don't know. It could be, it could be something like this, right? Or inside a trigonometric function, who knows? 5x cubed minus 2, right? Or forming the denominator. Or what if you have something like, which we are going to do, ax squared plus 4, right? Then you are going to take this entire thing. Here you will take this entire thing. The arguments basically of any sort of functions. So then you have to ask yourself, is its derivative. So if you're taking this as a substitution and then you take the derivative of that, is that also present somewhere in the integral? So for example, if I'm substituting this part, let me use the pointer. So if I'm making this substitution, so when this is a 4. So when I take the derivative of this du by dx, then that becomes 2x. So I do have a 2x here, not really a 2x, but now I do. So I can put a 2, introduce a 2, and then put an inverse outside of the integral sign. So now I do have the derivative of the inside function outside of the bracket, right? So you have to take those calls. Now, so this is the practical substitution test. So if I give you something like x multiplied by x squared plus 4 to the power of 6, and you have to integrate it with respect to x. The complicated part is this thing inside the bracket, x squared plus 4. So how do you fix that? Its derivative we know is 2x, right? So the integral does contain x dx, right? So now, although it does not really contain this entire 2x, but yeah, we can introduce something or the other in order to convert it into our desired form, right? Constants can be adjusted, right? It is close enough. So we will say, so now the technique starts. So you are going to substitute this inner function as u, and now you're going to take, because now if you're going to put u here, so this is going to become u to the power of 6, and there's an x, and there's an integral sign, and there's a dx here as well. Of course, now you have got a you have got an x, and you have got a u, and you are integrating u with respect to x, which doesn't make sense. You ought to have just one variable in the integral, because in the calculus 2 course which you're going to study in your university, you're going to do all of that, not here in your A levels, okay, or even in further math you do that. So now du by dx is going to be equal to 2x. And now let's see something. I do have a dx here and a dx here. So why do I not make this a subject, right? And try to get rid of this dx from the integral, because this is irrelevant, because now we have got a u here as well. So we can only integrate u with respect to x, okay? So now this becomes what? This becomes x times u to the power of 6, and dx is going to be du upon 2x. Now see something. If you did not get a 2x here and you did find a du here, and you are unable to cancel the x's out, then again it would have been a problematic deal, right? So now what do I see here? I see x multiplied by u power 6 with respect to u, and there is a 2x here as well, so I cancel it, I take the constant out, so this becomes half of u power 6 and du, and that's it. And now you're going to integrate it, and this is going to become u power 7 divided by 7 plus c, and then you're going to substitute the u back, which was x square plus 2 or 4, what was that, plus 4. So x square plus 4 to the power of 7 whole thing divided by 14, right? You couldn't have figured that out from here, okay? You couldn't have done that unless you did those substitutions. You wouldn't have figured that out, okay? So that's the reason we do it. Now you can verify that we did the right thing by taking the derivative of this. You take the derivative of this entire thing, and you are going to land here, and this is going, I'm pretty certain about it, you can check it. Now this is why substitution is often described as reversing the chain rule, right? As you would have observed, and you would have only observed if your chain rule differentiation is really good. If it's not, then you need to go back and revisit that as well, and for that you can watch our previous lessons. It's in one of the videos from last week. Now students sometimes do write u is equal to x square plus 4, which is good enough, and then continue working mainly in x. So if you're going to do that, it's not going to work, because now you have to, when you're making a substitution of introducing another variable, now you have to integrate that variable with respect to itself, right? Because otherwise it defeats the purpose. A proper substitution should remove the original variable completely. Once we introduce u, the integral must become entirely an integral in u. It must become a function of u and be integrated with respect to itself, right? So this is incomplete if you're writing down x u6 and dx, or maybe x u6 and du. I mean, it doesn't really make any sense mathematically, right? So this is what we're trying to say. Now one variable, one differential, one standard integral, that's what you need, and that is the standard you should apply to your own working all the time. Now let's try to do an example which has an exact derivative outside. So if I give you 3x squared minus 5x plus 2 to the power of 4, and of course you cannot spend your entire 45 minutes expanding it in the exam, and you see that there is a 6x minus 5 multiplying to it, and you're asked to integrate this entire messy expression with respect to the variable x. Now if you were intelligent, and I am sure you are, you would see through it that this inner function has a differential present already here. So the differential is 6x minus 5, right? And this becomes a 0. So this is 6x, the differential, this is minus 5, and this is plus 0. So 6x minus 5 is already present here, right? So what you're going to do is you will say that, okay, this function, let's say this is f of x, and right here is f prime of x, and this is some power 4, right? So you will say that, okay, this is a chain rule, a classical chain rule example. So we are just going to undo that, right? So how do you do that? So we are going to substitute this as u. So this is going to become u is equal to 3x squared minus 5x plus 2, and du by dx is going to be equal to 6x minus 5, and I can now rewrite it as 6x minus 5 is copied down as it is from here. This becomes, this entire inner expression under the power is nothing but u, because we just made the substitution and we put the same power here, and now dx will be substituted by du over 6x minus 5. Now this 6x minus 5 will be cancelled with this, and now you have u power 4, and you have to integrate it with respect to u. So this is nothing but u power 5 over 5 plus a constant of integration, and now you can substitute this entire messy looking function back, 3x squared minus 5x plus 2, and raise it to the power of 5 and divide it by 5, and that is the final answer. Okay, it's as simple as that. So this covers your entire integration by substitution, but we will do a little more into it. And this is the cleanest form of a substitution question, by the way. Cambridge is effectively placing both the inner function and its derivative in the same expression and testing whether you notice the relationship, and you must be vigilant enough to do that. Now let's do an example where a constant must be adjusted, right? Like we did in the earlier example. So if you have an x here, and let me change color in order for us to make the distinction between two different questions. So if there is an integral, if you have to integrate this messy looking expression with respect to x, then of course I can see that the differential of this is 4x. But I don't have a 4x here. So what am I supposed to do? I'm going to introduce this 4 here, and I'm going to introduce this 4 here in order to nullify the effect, right? So a constant inside and outside the function is the same, right? So this becomes, now if I make the substitution, this is u 2x squared plus 7, and this becomes du by dx equal to 4x, and we are going to do exactly that. So 1 upon 4 stays here, and 4x stays here, and 2x squared plus 7 becomes u, this is 5, and dx is going to become du upon 4x, and I'm going to cancel 4x with 4x, and now I can simply go ahead and integrate this, which becomes u 6 over 6 plus c. Make sure that you're not really ever forgetting this arbitrary constant of integration, because otherwise you're going to miss all the families. You're just going to be assuming that this has a constant at the origin, which of course may not be the case, right? It may start somewhere else, right? Now, so this is a 4, by the way. So this is 1 upon 24, and u was 2x squared plus 6. As per the substitution we made here, this is a 6, and this is a plus c, a constant of integration. Very important, right? And that's it. The most common error is to write this entire thing and forgetting to differentiate. The bracket produces an additional factor of 4x, right? This one, right? Don't do that. Always check your answer by differentiation. Make sure that you are verifying it by, differentiating it again and landing at exactly the same question. Okay, now let's say that okay, so there are also cases where the expressions are in a quotient form, in a fraction form, and then you have to make the substitution. So for example, and that's where logarithm comes in, right? Because just to recap, the differential of this logarithmic function, if I introduce the differential operator, is nothing but 1 upon function into differential of the function, right, in the numerator, and right. Now the reverse of it, so if you don't have it and you have something where the differential is in the numerator of an expression of a function which is in the denominator, right? So in such a case, you're just going to write ln function, right? And of course the entire families of it, so you are going to put a c here as well, unless you have some initial condition given in order to lock a specific function. Okay, now let's try to do a question. Let's say that you're given 6x plus 1 in the numerator. Let's say if this is going to form a nice question, and then 3x squared plus x plus 8. Okay, now I can clearly see that this thing is what? It is simply a function which has its derivative present in the numerator. So I can make the substitution of this denominator, 3x squared plus x plus 8, which is going to produce du by dx as 6x plus 1, and I'm going to now make some substitution. So this is 6x plus 1 over u into dx is going to be du over 6x plus 1. I'm going to make the cancellations, and now I do have 1 upon u du, which is nothing but ln u plus c, and u is going to be equal to 3x square plus x plus 8. That's it. And plus c, of course, right? And this is your answer. It's as simple as that. This is a recognition question. The algebra is very short once the structure is identified. Okay. All these questions you can find in your Cambridge Indoors textbook, the digital copy of which is available with me. You can WhatsApp me for it, +92329 3028485. I'm also going to put a lot of content. I always do every day on my Instagram channel as well, where we go by the name of EASY Taleem, TALEEM. Okay, let's get back to the lecture. Now, when the numerator is not exactly the derivative, for example, if you have an x here and there is, or let's say you have a 2x here and you have 3x square. Okay, let's not complicate it as yet. Let's do something like x upon x square plus 6x plus 10, and we are integrating it with respect to x. Now, you can see that the denominator has a differential of 2x plus 6, right? But 2x plus 6 is not present in the numerator. So let's do a few adjustments to the numerator. So how are you going to deal with that? Let's do that. Because the numerator is only x, so a direct substitution does not yet work cleanly. So we will rewrite x in terms of 2x plus 6. Okay. Now, so x is going to be equal to half 2x plus 6 minus 3. Right? Can you see that this is, so what I'm doing here is, so 2x plus 6. So if I have to put 2x plus 6, so this is what? So this is 2x plus 6. If I divide it by half, this is going to give me what? This is going to give me x plus 3. But then I have to cancel it as well. Sorry, my gadgets were running out of battery, so I had to plug that in real quick. Okay, so this is how, so this is equivalent to, so what am I doing? So there's a 2x plus 6. I first of all divided it by half, and then I subtracted 3 from it as well. Okay, can you see? So now I have it in terms of the derivative. So I can rewrite this x as half times 2x plus 6, which is the derivative of the denominator, minus 3, upon the denominator, which I can substitute as u, which is x square plus 6x plus 10, right? So I will just write u here, and this dx may be rewritten as du upon 2x plus 6. Okay, so 2x plus 6, and now I put the integral sign here. Now what do you have to do? So now this is, I can break this into two terms inside the integral sign. So this is half of 2x plus 6, the entire thing divided by u, minus 3 upon u, the whole thing getting integrated with respect to 2x plus 6. Okay, and there is an integral sign. Now you can see that we here have what? So here we have integral of, so I'm not going to separate it, half of 2x plus 6 upon u into du over 2x plus 6, right? And then integral of 3 upon u into du over 2x plus 6, and maybe I will put this, I'm just going to go back to x, right? So du upon 2x plus 6 is nothing but dx, and u is nothing but what? It's x square plus 6x plus 10. Okay, x square plus 6x plus 10, because I'm going to introduce another arc10 integration as well, inverse of 10, right? So let's do that. Now this cancels this. Sorry, the half wasn't here. Now I'm taking this half outside. So this becomes half of, this becomes ln u plus c, or I'll introduce plus c towards the end, and u was what? U was x square plus 6x plus 10. And now this is what? Now if I quickly do a completing the square form. So this becomes what? This becomes x plus 3 whole square minus 9 plus 10 is nothing but plus 1. So now I can make another substitution. So this is 3 upon x plus 3 whole square plus 1. Now I will make the substitution. Now this u, another substitution, or p, or rather let's just say u, because we have already dealt with u here, it's no more present there, so I can again introduce this. So this is x plus 3. So now I have 3 upon u square plus 1, and du by dx is what? U square plus 1, and du by dx is nothing but 1. So I can rewrite dx as du, right? So, and I will just bring this back here, ln x square plus 6x plus 10. Now, we haven't done the inverse 10 integration so far, but I'm just going to write it here, and we are going to do it towards the end of this lecture. We are progressing towards that, right? So x square plus 6x plus 10, and this is minus 3 tan inverse of u, which is nothing but x plus 3. So I'm going to put x plus 3, tan inverse of x plus 3, and the constant of integration. So that's your answer. Yeah, it may look intimidating because we are covering a lot of topics here, but with a lot of practice, and if you if you pay attention to what I always say, that you go back to your Cambridge Indoors textbook and do all the exercises and a lot of practice in order to master this, right? Now, this question is useful because it combines what? Algebraic rearrangement, logarithmic recognition, completed a square form, right? Completing the square form, and inverse tangent recognition and integration of that, which we are going to do later. It also shows that substitution is sometimes only one step in a longer solution, right? Because the solution was quite lengthy, substitution was just one step. You first identify, intelligently decide what expression to substitute with what, take the derivative, and then replace the dx with du. Okay, now let's move to the inverse tangent pattern, which we just did, and now let's learn how we do that. Now you need to recognize that the differential of, okay, let me change color. So the derivative of tan inverse x is what? It is 1 upon 1 plus x squared. Okay, so I hope you know it already, because see, if I take tan inverse of x, and how do you prove this? So if I take tan inverse of x as u, and now if I the previous step of this would have been x is equal to tan of u, right? Now if I implicitly differentiate it, right, and we have done implicit differentiation in the previous lectures. Now if I implicitly differentiate it with respect to x, what do I get? Let me put it here. So d upon dx of them both. So this is nothing but, so this is, and don't forget that u was tan inverse of x, or x is equal to tan u, right? Don't forget this. Now this is 1, this is sec square u, and because we are differentiating u with respect to x, we are going to put dx here as well, right? Now this becomes what? So 1 upon, so dx is going to be equal to 1 upon sec square of u, and sec square of u is what? 1 plus tan square of u is sec square of u, right? We have done this identity in in trigonometry, right? So I can rewrite 1 plus tan square of u is going to be dx, and dy by dx, sorry, not just dx, dy by dx, du by dx, my bad. So this is du by dx. So now tan u was x, so tan squared u is going to be 1 plus x squared. So 1 plus x squared is nothing but du by dx, right? So hence we showed that the differential of the, and u was what? Tan inverse of x, right? So in place of u, I'm going to write tan inverse of x, and now we have proven that the differential of tan inverse of x is nothing but 1 upon 1 plus x squared. Can you see? So when we had 1 upon u, so if I took this 3 outside, if I put it here, so now I have 1 upon u squared plus 1. So this is nothing but tan inverse of u, right? as you can see from this definition. Right, I hope it's clear now. Or you can rewind and try to do, or try to replicate all these steps that I'm doing, or play the video at 0.5 or 0.75x speed in order to understand it better. Okay, so let's do a general form of this arc10 integration. So if you have and let me change color. So if you have something like 1 upon a square plus x square, integral of that with respect to x, you can simply rewrite it as 1 upon a tan inverse of x upon a plus c. So you can convert anything of this sort. So this is a constant squared. So for example, even if you have 1 upon 3 plus x squared, for example, so you can convert it into 1 upon under root 3 whole square plus x square dx. So this is going to convert into 1 upon under root of 3 tan inverse of x upon under root of 3 plus c, right? As simple as that. Now let us derive that instead of simply memorizing it, right? Now, so if you had to evaluate 1 upon x squared plus 25, so 25 may be rewritten as 1 up 5 squared, right? And you have to evaluate it, or integrate it with respect to x. So first of all, what I can do is I can factor out the 25. So this is going to become 1 upon 1 plus x upon 5 whole square, right? I hope that makes sense. Now we are integrating it. So whenever we had a constant here, we derived it for a constant 1. So now this is nothing but 1 upon, so now let us first make a substitution here. Okay, so we can say that u is equal to x upon 5. So du by dx is going to be equal to 1 upon 5, or dx is going to be equal to du upon 5, right? Oh, sorry, dx is equal to 5 times du, my bad, 5 times du. Okay, so now this is going to be equal to 1 upon 25 integral sign 1 upon 1 plus u squared. Dx is going to be equal to 5 times of du, so 5 cancels this. So this is now 1 upon 5 1 upon 1 plus u square with respect to u, and we already derived it. We saw the antiderivative, so that's nothing but tan inverse of u plus c, and u was x upon 5. So we are going to put that here as well. So x upon 5 plus c. And by the way, you can do this general proof with a square plus x square as well, right? Okay, now let's try to do a shifted quadratic through it as well. Now, if you have, and again, let's change color in order to make that distinction. Let's do red color. Okay, so if you have integral of 1 upon x squared minus 4x plus 13 with respect to x, so I can convert it into 1 upon x minus 2 whole square minus 4 plus 13 is plus 9, and with respect to x. Okay, now using the inverse tangent form, I can rewrite it as, so first of all, u is equal to, now actually let me just give you, so this is 1 upon 3 squared plus, or I can first of all factor the 9 out. So this is 1 upon 9, and this is 1 plus x minus 2 whole squared upon 9, right? And this is dx. So which can further be rewritten as 1 upon 9, 1 upon 1 plus x minus 2 whole square upon 3 square, which I can rewrite it as, I can convert it into a single fraction x minus 2 over 3 whole square, right? As simple as that, and dx. Now you can just simply integrate it. So this is going to be, so u is equal to x minus 2 over 3, and so du by dx is going to be equal to just 1/3, and du is going to be equal to, or thrice of du is going to be equal to dx. So this is nothing but 1 upon 9, 1 upon 1 plus, we substituted with u squared, dx is going to be equal to 3 times of du. 3 cancels the 9 in the denominator with a 1/3, so this is 1/3 of 1 upon 1 plus u squared du. Now this is our familiar form, and we can simply do the integral as 1/3 of tan inverse u, and u is going to be equal to x minus 2 over 3 from here and plus c, and that's it. A large number of inverse tangent integrals only become visible after completing the square, so make sure that you are not trying to do that directly. That is why your algebra remains important even in calculus, right? So if your base is strong, if your AS concepts are strong, then I mean you are winning. Okay, now if I ask you to integrate an exponential function, let's say you have e to the power of 2x plus 3, and you have to integrate it with respect to x. Now this can be done directly, but it is still substitution in principle. Now how do we do that? Now this is like I said that this can be done directly, but it is still substitution in principle, and I'll show you. So we already did this in our last lesson. This is nothing but you keep it as it is, and you divide it by the differential of the power, which is 2, and you put a c here. Now let's see how we can do this through substitution, or how this result is actually derived from substitution. Now let's assume that this, or let's substitute the power by a single variable, that is u. Now u, so du by dx is nothing but 2. So du, so half of du is going to be equal to dx, right? Now this is e to the power of u dx. Dx is nothing but half of du. Half of du, I will take this half outside of the integral sign. So this is half of integral of eu with respect to du, which is nothing but itself. So this is half of eu plus c, and u is nothing but 2x plus 3. So I will put it there, and that's it. Bam. You got your answer, right? Okay, now let's try to do the question that I put up in my stories. Let's say that you have x times exponential to the power of x squared dx. Now you can see that the differential of the function in the exponent, in the power of exponent, is already present here, or something of that sort is present here, right? So I can substitute this. So this is u is equal to x squared, and du by dx is going to be equal to 2x. And now this becomes x times e x squared. X squared is u, so e to the power of u. Du is nothing but dx is nothing but du upon 2x. I'm going to cancel the x with another x, and now this is going to become 1 upon 2. This 2, I bring the half outside of the integral sign, and this is eu du, which is nothing but half of eu plus c, and eu is nothing but exponential to the power of x squared plus c. That's it. Okay, so this is as simple as that. These two integrals look similar, but the reason for choosing the substitution is different. In the first, the exponent is linear. In the second, the derivative of the exponent appears outside. Okay, now let's do substitution with trigonometric functions. So still we are under the umbrella of substitution, but let's do a type of it that is under trigonometric substitution. Now, sub trig, give the heading and start taking down notes. Okay, now, so if I give you, or if you come across an integral, an expression which needs to be integrated, which is something like sine x times cos x to the power of 4, and you have to integrate it with respect to x. Now you can simply see, so you know the integral of this, you know the integral of cos x to the power of 1, but you don't know the integral of cos x to any other power. So in such a case, what I can do, and you know this thing, that this may be rewritten as cos x to the power of 4 dx, right? Now what did we say? We said that in such cases we substitute what is inside the power, right? And we can also see that the differential of this inner function is already present outside of the power, right? So let us substitute cos x by u. So du by dx is going to be equal to negative of sine x. Let's keep it as it is, and now let's start substituting. So sine x stays as it is, gets copied down. Cos x is nothing but u raised to the power of 4. Dx is nothing but du upon negative sine of x. Make sure that you're not making the blunder of forgetting the negative sign. Now sin x cancels with sin x, and I'm left with negative of integral of u to the power of 4 with du, which is nothing but negative 1 upon 5 u5 plus c, and this is negative 1 upon 5, and u is nothing but cos power 5x plus c. That's it. This is the foundation for the higher power trigonometric integrals we will study later in this very lecture. The important question is not, is this a trigonometric integral? The useful question is instead that can one trigonometric function become u while the other supplies its derivative the way this cos x supplied the derivative for sin x, right? Now let's do another example so that the concept is anchored well in your heads. Now again, let's change color. Let's use this one. So if you had to evaluate cos x times sine 6x dx, so now let's substitute sine x with u. So du by dx is going to be equal to cosine of x. Now let's make the substitution. So cos x times sine x, sine x is u, so u to the power of 6. Dx is nothing but du upon sine cos x from here. And now I'm going to cancel cos x with cos x. So I'm left with integral of u6 du, which is nothing but u7 upon 7 plus c, and u is nothing but sine. So sine 7x over 7 plus c. That's it. Just under 15-30 seconds you can evaluate it. Now, how do we do the definite integration by substitution? We just apply the limits, right? Definite integral is always with the limit. Make sure that you never forget that. So if you had to integrate this one, x times x squared plus 3, where this 3 is inside the bracket of power 2, and you have to integrate it from 0 to 1. So know that this function, so here what are we doing? That this, we have a function. Okay, so this is a power 5. This is a polynomial of degree 5. So we have this function and we have to find the area under the curve and the x-axis from 0, x is equal to 0 to x is equal to 1. However, let's not get into that. Let's just focus on how to do it algebraically, right? So there are two valid approaches. Now, first of all, we return to x, right? We take the substitution. We said that u is equal to x squared plus 3, which is the function inside of the power. So du by dx is going to be equal to 2x, and then we start making the substitutions, not forgetting the limits. So this is going to be equal to u squared, dx is going to be equal to du upon 2x, and we are going to cancel this x with x, and I'm going to be left with half goes outside of the integral sign, limits goes as it is, and this is u squared du, which is nothing but half of u cube over 3 plus c, and u is nothing but, u was x squared plus 3, so x squared plus 3, and there is a power 6 here, and there is a plus c, so don't forget that. However, the question is, however, we are not going to put a plus c here because we are going to put our limits 0 and 1, right? So now I'm going to put 0 and 1 here the way you used to do in your AS level. So this is going to become, I can take this 1 upon 6 sign outside of this modulus. So this is going to become 1 upon 6. And now I'm going to put the limits. So 1 plus 3 is 4. 4 to the power of 6. Is that 6? No, this was a 3. My bad. This was a 3. So 4 to the power of 3, which is 64, negative. And then I put 0. So 3 to the power of 3, which is 27. So 64 minus 27 is going to be 37, right? So 37 upon 6 is going to be the answer or the evaluated numerical value. So 37 upon 6. Excuse me. Now, the second form is, which you are going to use a lot of times, is that we change. So the question was x times x squared plus 3 to the power of 2 dx, and the limits was from 0 to 1, and the limits, make no mistake, is an x, is when the variable is x. So these are the limits of the variable x. So this is x is equal to 0 and x is equal to 1. Now, if I am making a substitution of u is equal to x squared plus 3, so du by dx is going to be equal to 2x. Now, so this is going to become x times u squared, dx is going to become du upon 2x, and there is 0 and there is 1, x cancels this. So now I am left with half times 0, 1, u squared du. Now I can apply the limits directly as well. I can just, instead of putting the u back here, because I need to find the numerical value of this integral, definite integral, right? So what I can do is I can change the limits, because right now this is incorrect, because this is x is equal to 1 and x is equal to 0, and our the entire expression is in terms of u. We have to integrate a function of u with respect to itself, right? But the limits are in another variable, that is x, right? So now let's change the limits. So let's put an x here and u here. So when x is equal to 0, u is equal to 3, and when x is equal to 1, which is this other limit, u is equal to 4. So the limits for u is from 3 to 4. So I can rewrite it as half is outside, this is from 3, u is equal to 3, and this is u is equal to 4, and this is u squared, and this is du, and I can now do it directly, and you will see that the answer is going to be same. So now this is going to be equal to u cube upon 3, and I can bring the 3 out, and the limits is from 3 to 4, right? So again, this is going to be equal to 64 minus 27. Again, this is going to be 37 over 6 square units, and that's the answer. Both methods are correct, but never mix them. Once you change the limits to u values, the entire working must remain in u. Do not substitute x limits into an expression involving u. Rewind it, listen to it again. If you are not doing it, I will again repeat it for you. Do not mix the two methods. Both are correct in their individuality. You can adopt either of them. However, once you change the limits to u values, values for a new variable, the entire working must remain in that variable, that is u. Do not substitute, and the second point was that you do not substitute x limits into an expression which involves the other variable, a substituted variable, that was u. That is one of the most common errors in definite substitution. Now, let's see a Cambridge style area application. So let's say that you're given a curve which is given by x upon x squared plus 4 whole denominator to the power of 2, and it says that x is greater than and equal to 0. Okay, now they're asking you, so we are staying on the right side, or on the right side of the y-axis, right, because of the domain restriction, or on the y-axis because x is greater than and equal to 0. So now the question is asking you to find the exact area bounded by the curve, whatever this curve's shape is. It could be anything, like, right, x by the curve, the x-axis, x is equal to 0 and x is equal to 2. Let's say that this curve is above the x-axis, right, whatever shape it may be, right? Now they are saying that area bounded by the curve. So first of all, we are saying that area bounded by this line, and then the second line is that by the curve, the x-axis, so x-axis is here, the lines x is equal to 0, so y-axis is the line x is equal to 0, and the other line which is x is equal to 2. So I draw that line as well. So basically we are talking about this region, right? And how do you do that? You basically integrate the function, whatever this function y was given, and put the limits from 0 to 2, and that's it. So you have already done that in ALevel. However, the function inside of the integral is now becoming complicated, right? So now let's do it. So area is going to be equal to a definite integral from the limit 0 to 2, where the numerator is x and the denominator is x squared plus 4 whole thing to the power of 2 and dx, right? Now I can quickly see that the differential of the inner function is present in the numerator, so I can apply substitution, right? So this is again only a matter of recognition. So now I substitute this inner function x squared plus 4 by u, so du by dx is going to be equal to 2x, and now this becomes from 0 to 2, x stays as it is, x squared plus 4 becomes u to the power 2, dx becomes du over 2x. I cancel the x, I take the half outside of the integral sign just for the sake of simplicity, and I will have u to the power of negative 2 and du, right? Now, I'm not changing the limits because it's not needed here. I don't want to do extra steps. So now this becomes u to the power of negative 1 over negative 1, and I can just put this negative sign here, and I apply the limits from 0 to 2. Now this becomes what? This is minus half, and this is 2 to the power of minus 1 is half, and then 0 is nothing, right? So I just put it here. So the answer is going to be equal to I think I made some error here. Let me just quickly check. Okay, yeah, I spotted the error. Dx was not du upon ta. Okay, could you see that the biggest error that I made was what I just told you not to do? I applied the limits of x in the variable y, right? Such a huge blunder, right? So if I'm not replacing u by x, I cannot apply these limits, but I can replace it by x. So this is going to become 1 upon x squared plus 4, and now I can use these limits, right? Or I can do minus half u to the power of minus 1 is 1 upon u, and now I can change the limits 0 to. So if u and x, so if x is 0 into y is going to become u is going to become 4 and 8. So now it has the limits from 4 to 8, and this is 1 upon u. So I can do either, right? And the answer is going to be same, you will see. So this becomes, so when I apply 1 upon 8 minus 1 upon 4, so that's going to become 1 upon 8 minus 1 upon 4 is negative 1 upon 8, which is nothing but 1 upon 16. That's the answer, squared units, make sure, because that's the area. And now this is minus half, and I apply these limits, so this becomes 1 upon 8 minus 1 upon 4 again, which is going to give you the same answer, which is 1 upon 16 squared units. Okay. Now, the Cambridge topical pack includes this broader style question where substitution is embedded inside an area problem rather than presented as a standalone technique. And you can go to Papa Cambridge and download that pack and do as many integration problems for practice as possible. Now, when does this substitution not work? So, for example, you have, okay, let's see. Let's change color. We are doing something new. New, not difficult, because now we have covered the entire substitution part. Now we are moving into the by parts part. Now if you're given something like e to the power of x, where this outside function is not a differential of the power of exponential, right? Now what do you do? A student may try to take u is equal to x and then find out that du by dx is going to be equal to 1. So this is going to be equal to x eu into dx is going to be equal to du. Now you have an eu, you have a dx, and you have been unable to cancel this x out. So you just saw that you cannot make the substitution. Another may try that you are going to take u is equal to x. So du by dx is going to be equal to 1. So this is going to be equal to so this x is going to be equal to u. E to the power of x becomes e to the power of u, and this becomes du. Again, you can, so since the way you could not integrate this, in the same manner you cannot integrate this, so we are stuck, right? However, mathematically we do have a solution, but the method we are adopting does not have it, right? So substitution does not simplify the integral here. That's an important conclusion. Not every integral containing two functions is a substitution question. This expression was generated by the product rule, right? Some product rule was applied to give you this. And it was not generated by the chain rule. Therefore, it will require integration by parts, which is the reversal of product rule, and which we are now going to start. Now, before using step substitution, run this check. Step 1. Identify the most complicated inner expression and see whether the differential of that is present outside somewhere, right? And substitute that. Step 2. Make sure you are taking a derivative. Make sure you are doing that. If you are not doing that, then you probably are integrating u with respect to the old variable, that is x, and that's a disaster. Step number 3. Replace everything including dx, right? You do not want a dx with a variable inside of it that is a u, right? So replace dx, very important. Step number 4 is that you check whether that derivative or a constant multiple of it is elsewhere in the integral, and we have checked the derivative. Okay, so I already told you about it. And make sure the transformed integral contains only u and du, right? So make sure that inside of it you have a function of u and you are integrating it with respect to u, nothing else. You shouldn't have an x here, not here, not here, and not in the limits either, right? So it has to be in one variable only. And then Step number 6 is pretty straightforward. That is, you integrate, right? Because you have done all the hard part, now you just have to do the easier part. Now, for an indefinite integral, you must return to x. You shouldn't, because there are no limits to change, right? So you must come back to x. But for a definite integral, either you can return to x and use the original limits, or you change the limits and you stay in u, right? You can do either, and we have done multiple examples here in the lecture, and we saw that the final answer was the same. Now, step number 8 is that you differentiate your final antiderivative to verify it. Whatever answer for the indefinite integral you got, you differentiate it again and see whether you are landing at the same expression which your question gave you. Okay? Now, the way you would solve simultaneous equations and find a coordinate and see whether the coordinate that you found satisfy both the equations that you solved simultaneously to attain that, right? It's the same process to verify it. It's just a good practice. Now, I want you guys to pause and attempt these. Question number 1 and leave the answers. You can DM me on our Instagram, which is Easy Taleem, EASYTALEEM. I'm going to respond to everyone. 3x squared x cubed plus 5 to the power of 4 dx. Give me the answer of this. Let me give you another one. 4x upon 2x squared plus 7 dx. I hope you can identify which needs to be factored out, right? That's very important. Or whether there is a derivative present in the numerator of the function in the denominator, or the expression in the denominator. Now, find the definite integral of, from the limit 0 to pi by 2 of sine x cosine cube x with respect to x. Now, integration by substitution is not a formula. It is a method for recognizing that an expression has been created through the chain rule and then reversing that structure. The practical clue is a function appears and its derivative appears somewhere else in the same integral. Just like this function appears, you substitute it, you take the derivative, it's going to be negative sine x. Sine x is again present here. You can do the cancellation, you can change this dx, and then you can integrate it, right? So, but now consider that if you have x multiplied by e to the power of x dx, there is no inner function whose derivative solves the problem. So the reversal of chain rule doesn't help here. So hence we cannot invoke the substitution method. This integral comes from a different differentiation rule, which is the product rule. So in this part we will reverse the product rule and derive integration by parts from first principles. And I think we can, I mean, this integration by parts, I can do it in this very video as well, but then it is going to become very lengthy. Already we are at 52 minutes, so I think I will make another video for that, where we are going to see how do you integrate these terms, x sine x dx and ln x dx. Looks simple, but unless you are using integration by parts, you cannot do that. So if this lecture helped you, like the video, subscribe to the channel, share it with someone who's appearing with you for the resets in October, November 26, or in May, June 27, if you're moving from AS into A2. And if you need if you need any sort of structured support, our batches are starting from the 1st of August for the regular batch for May, June 27. But if you are resetting, if let's say, God forbid, you do not get the result that you desire on the 11th of August, then we are launching our crash course on the eve of the 11th of August, and you can enroll in that. So you can reach out to me on our Instagram, which is EASY easy Taleem, TALEEM. Taleem means education, and or on our WhatsApp directly +92 329 3028 485. I'll see you guys in the next lecture, where we are going to complete this integration bit of calculus, where we are left with integration by parts, and we will also cover the trapezium rule, which is very basic. So I'll see you guys on Monday, hopefully.